presentation. I first would like to thank CASP organizer and the assessor for inviting me to present my work here. So to answer Gabriel's question about what's the difference between our method and other methods, as others have presented, I'd like to briefly overview what I have seen in this CASP. I see 4 different kinds of methods. One is energy and potential-based methods. Basically try to calculate the energy and the potentials of plotting complex models, then evaluate the quantity. I see more and more methods using machine learning to predict the global and the local quantity of assembly models. I also see some methods use a geometric similarity between models to assess their quantity. And finally, there are kind of methods that combine these scoring metrics in order to improve quantity assessment. So our method, Multimer QA, is a hybrid method, try to combine different scoring metrics with a new design and implementation. So we are new to this field, so we draw the lessons from the tertiary structure prediction in order to design this coordinate structure prediction method. So basic idea is the most important lesson we learn from the tertiary structure prediction is the similarity between one model and all other models. The average similarity is a very important indicator of the quantity of that model. These consensus-based models actually work well for many targets. So why does this work well? I think it's rooted in a philosophical foundation. That is, there's only one way to be correct in this context, such that good models are similar to each other. But there are many ways to be incorrect. That means incorrect models tend to be dissimilar to each other. So when we calculate the average similarity of the good models tend to be higher than average similarity of the better models. So based on this, we design our first key score of our method is average similarity. Basically, for given a pool of models, we use MM9 to calculate the TM score similarity with other models except itself, and then average them as the first key score of our scoring metric. Okay, this works well for many targets. However, it has one significant weakness. It's going to fail when there are too few good models in the pool for a harder target. And when better models are quite similar to each other. So then in this case, better models tend to have higher average similarity than good models. We need a countermeasure to correct this weakness. So we design a single model interface context score predicted by deep learning to complement these consensus scores. So here's how we calculate the interface context score. So given any interface in the Multimer, for 2 chains, we use deep learning to predict the context probability map. Then for each context in this interface, we find its probability, then average them. So we get an average interface context score as another scoring metric. So we use a deep learning method developed by us called a CD-pred to predict the interchain context. So basic idea is given any 2 interacting chains, we get the sequence, we generate the sequence for this timer, and then use co-evolution analysis and particularly language models to calculate the inter-registry attention interactions as the input. We also get the tertiary structure for each chain using AlphaFold, then calculate the intra-chain distance map. These 2 information are combined, used by a deep neural network, consists of convolution layers, residual networks, attentions, all those kind of elements to predict the distance between any 2 amino acids. That distance will be converted into context probability map. So this method is substantially more accurate than any existing methods in the field. So we use it to calculate the interface context score. Now, before CASP, we did an experiment to compare the average pairwise similarity score and the interface context score to see how well they work on ranking CASP15 multiple models. So we use a lot ranking loss to compare them. Ranking loss basically is TM score of the best for that target, or best model, minus the TM score of the top 1 selected model by each metric, right? So we can see how good they can rank those models, smaller, better. So the baseline method is basically Ali Olofsson's methods, just count the number of contexts in the interface. You just use that to rank models. Actually, you get a loss about 0.3. And if you use interface context score, average probability of the interface context, we reduce the loss to around 0.2. Then average pairwise similarity is substantially even better than interface context score. It actually reduces loss to about 0.12. Then we try to combine these two things to see whether or not we can get further better results. So we combine them, average weight of these two, context score and the pairwise similarity score, we further reduce the weight, reduce the loss. So we use these as our method for the CASP15. So here's the pipeline of our method. So basically give a pool of a target for models for a target, stoichiometry, sequence information, monomer structures, and other information. We calculate the average pairwise similarity between one model and other models, and also the interface context score. And finally, we combine them, average weight as the overall global quality score. We also use this interface context score as the interface score, similar to the CASP. Now, that's our method. Now I'd like to summarize our results. So we use two metrics to evaluate our method. The first is the Pearson's correlation between predicted score and true TM score of each model. We calculate the per target correlation. Then we plot those correlation scores for all the targets here. We can see for most of models targets, actually the correlation score are pretty good, higher than 0.75. But there's some bumps here that represent the small group of targets that have the lower correlation score, particularly even some of them have the negative correlation scores. So I label those targets here. The second metric that we try to, that means they failed on those targets. The second metric I use to evaluate this method is ranking loss I just described. So we calculate ranking loss for each target and then plot them. So we can see ranking loss, most of the targets have pretty low ranking loss, less than 0.1. But there are a couple of them you see have the higher ranking loss. Even some of them actually has a very high ranking loss, 0.4, 0.5, something. The red, actually, many of them actually have lower correlation scores, those targets. The red ones corresponding to some lower correlation score targets. And there's some strong correlation between these two metrics. Actually, the matrix correlation between the target correlation scores and loss is about minus 0.84. Okay, that's the overall results. Now, let's look at some specific examples to say when this method succeed and when this method failed. Here's one first target. It's a very large complex. It's like this ring-like structure. So if we can plot the true GTD score of all the models for this target, it's a very wide range of the scores. But in this bin, these models in this bin actually has very high quality. And then if we use our methods, we select the one from this bin and has a loss about 0.03. This is the best model, and correlation score is median, it's 0.62. So this considered a successful example. And we expect this work because the consensus, right? There's a large group here, good models here. It has a higher average similarities than all others and the interface context scores. That's meet our expectation. Here's another one. This is a dimer. So there's a true structure, best model, selected model. It's a wide range of distribution of true scores, and it's able to select a model from this small bin with the highest quantity, average quantity. So you select here, and also loss is very low. Correlation also is very high for this one. Both metrics actually works pretty well. Here's another one. This one is very important. This one I consider the most important target in this CASP competition. Why? Because this has many chains, and the sixth chain has 7 ab initial domains. If you cannot select the right complex for this one, you can never do well in the tertiary structure prediction. Not only for your complex structure prediction, but also tertiary structure prediction. So this one is extremely important. So you can see distribution of the scores, wide range of scores. There are some people managed to make very good models with this straight tail, very important, not bended, it must be straight. And our methods actually select the model, very good model from the second bin with very high scores and 0.87, a little bit less than top model, and the correlation also is very good. So I can, even though it has not been able to select the best one, I think the loss is acceptable for this one. Okay, So here's another one. Here's another dimer. And this one is the interesting one because it shows that how interface score actually improve the pairwise ranking. Here's the distribution of the score of all the models. If we just use average pairwise similarity to select a model, it's going to select one from this bin, the yellow one, score 0.85. But use interface average of them, we get actually this one has even better quantity, is a reasonable quantity. So the loss is 0.06, and even the correlation is very low for this one. So, but ranking is successful. Finally, I'd like to show you one example why this method failed. This is a typical example. This is an example that already we see a lot of discussion about this one. And T1122. Here's a tree structure. The tree structure has a two interface A, interface B. But here's a distribution of the true scores of most models submitted for this target. You see, there's one bin here, has many models clustered in this bin. They have mediocre quality. These models in this one are very similar to each other because AlphaFold just generates these models, a lot of such models in the pool. So they are very similar to each other, but they are not the best one because they only capture one interface, ignoring another interface. So that's a problem, means interface need to be seriously considered in this one. But this causes a big problem for our methods because the models in this pool, this bin is very similar, right? Very similar. So they have higher average similarity that mislead the consensus score. That's why it failed. And this, I also see some other these kind of cases. So this is a typical failure. That's what we want to address future. How do you correct this weakness? Okay, maybe also ask another question. So how your method may work if you know how models are generated, right? So if the model knowledge is known, can your method still work? So we test this approach on the CASP models we generated, in-house models for the CASP targets. So we use average score, average of pairwise similarity, and the PLDD score, AlphaFold's PLDD score to rank models. We also just use AlphaFold's confidence score to rank models. Average of the pairwise similarity and AlphaFold confidence score versus just AlphaFold confidence scores. So we plot them, plot the loss of one metric against another one. You can see for most of them, they have very similar models with a similar quality. Loss is very low. But there are some targets that AlphaFold's confidence scores do better. There are other targets that average score does better. So that means these two are complementary each other. We didn't see significant difference between the two. The reason is that all models are more similar to each other than less diverse than the CASP models submitted by all the CASP predictors. So diversity also is important for consensus approach to work. So with that, now I'd like to summarize the challenges I think we encountered in this CASP experiment. First is that we found that it's harder to align the very large Multimer models because the chain order matters. Sometimes MMLine produce different similarity scores when you change the order of the chains. So Gabriel said that, as Gabriel said, he figured out a way to generate the optimal mapping. So this problem have been solved by this CASP. Another is we found that assembly estimation of accuracy is more complicated than other methods because than tertiary structure evaluation. The reason is that we need to consider both tertiary structure quantity and the interface quantity. Those are two factors need to be considered. That's different from tertiary structure evaluation. And of course, there are fewer machine learning tools to assess the quality of the interface and the accuracy. We have fewer methods to effectively combine different scoring metrics. So here's my conclusion. So the pairwise similarity score is very useful metrics for assessing the quality of the assembly models, but it has a significant weakness. And interchain context prediction can be used to estimate the accuracy of the interface in the Multimer models and also assess the quality of the assembly models. And more scoring metrics are needed to correct the weakness of the pairwise similarity scores, and better approaches for combining complementary scoring metrics are needed. Probably we need to develop deep learning methods to do this too. With that, I'd like to thank my students who did this work, and Jen actually is attending this conference, and thanks funding agency for supporting this research, and thank you very much for your attention.
Thank you, Jianlin.